Hello, everyone. Good afternoon. Greetings from E2MoC. Welcome to the academic seminar program year 2025 of the E2MoC Research Group here at the Aeronautical Institute of Technology, ITA. I thank you all for virtual participation here this day. I'm a Professor Wheeler from the Space System Department here at ITA, founder and coordinator of the group, and also member of the ITA Space Center. In addition to me, we have Professor Liana from INPE, Professor Marcio here from ITA, and the PhD student Isabella, also from ITA, here in the coordination of the E2MoC. Our group, just to let you know, that our group was founded on March 2029, and it's our goal is to contribute to the progress of research and development in the space sector in Brazil, specifically in the areas of space system engineering, orbital mechanics, and aerospace vehicle control. Our seminars aim to publicize the work carried out by our group members and research from other institutions. We also have our YouTube channel where recordings of the lectures are posted. We have several very interesting lectures from past seminars on our channel. It's worth checking out. Other channels for publicizing the group's activities are Instagram, LinkedIn. We have our website, e2moc.ita.br, but it's currently under maintenance. And the WhatsApp group, where opportunities, scholarships, and news from the space sectors are shared there. If you would like to join the WhatsApp group, please send us an email at the e2moc@ita.br. And we are also have an email distribution list that you can ask to join. So our seminar works as follows. Let me know you about the dynamics of our seminar. We have around 1 hour or less for the presentation of the presenter, the lecturer. And in the following hour, we will open for questions and answers. Questions or comments can be made directly to the speaker by clicking on the little hand below here in the Google Meeting. And when prompted, turning on the video and microphone or writing the question or comment in the chat that I will read for him. So we ask you that you keep your mic off during the presentation to not disturb the lecture. And so for this seminar, we are pleased to welcome Dr. Josh. I don't know how to pronounce your.
Usually folks say Lyzhoft, or that's how my family says. Don't even worry about it. I've heard it so many different ways, Willer. Josh is fine.
Okay, thank you. So he's a space engineer at NASA Goddard Space Flight Center, and he will please us with the lecture, A Look into Planetary Defense. Just a brief introduction about Josh. He's a aerospace engineer specialized in planetary defense and small body proximate operation. He earned his PhD in space engineering from Iowa State University in 2017, focusing on hypervelocity asteroid intercept guidance systems under the mentorship of Dr. Bong Wee. In 2016, Josh joined NASA Goddard Space Flight Center, where he contributed to the Double Asteroid Redirection Test mission by working on binary asteroids dynamics. He also played a role in the OSIRIS-REx mission, assisting with the interdependent verification validation (IV&V) activities from their approach phase through BINU departure. His research interests include developing terminal guidance systems for asteroid intercept missions, optical navigation, and onboard shape modeling. So, Josh, once again, thank you so much for accepting and taking time to give this lecture. I'm sure that everyone will enjoy a lot and will love your presentation here. So feel free to share your screen and start the presentation when you're ready.
Okay. All right. think that should work. Okay. Yeah, I wonder if I can actually navigate from here. No, okay, I just have kind of like a little marker that I can see. Okay. Yeah, so I'm Josh, Goddard Space Flight Center, and I'm going to go over a little bit about planetary defense and some of the workings, I guess, that I've been a part of. So that and some of our research that we're doing at Goddard. So, and I think it'd probably be best to hold questions towards the end, just, I guess, so it's a little bit more organized. But if there is something, raise your hand like Willard said, and we can get it answered straight away. Okay. Okay, let's see. All right. So this overview, we're going to just kind of go over planetary defense, nutshell, go over some missions that we actually, or that I was a part of. Of course, there's not many actual planetary defense missions. We have only one. But I'll kind of talk about that. Some research I got, like I said, and then some more of my work, which is tied into, obviously, the stuff that's done at Goddard, and then a wrap up for questions. But just to kind of start off, the picture that you see here, or the image, is our Arecibo radar imaging of the Dynamis system, where we're seeing that we have this binary system. It's really exciting. We couldn't really get much from it. But I'll kind of talk about that. It's just, keep this radar imaging in your mind. So when I talk about some of the shapes and things like that, we'll kind of get an understanding. Because if you see here, we're kind of looking down on the orbit plane. So anyway, so our current asteroid discoveries, we got a lot out there. This is just kind of giving a little example of what's going on, kind of our discovery rate as the years have been going on. So you can see we have been discovering a lot more asteroids as we go on. Now, we don't really know how many are out there. We have our different models, statistic models that say there should be this many, and so on and so forth. But we will have some future missions that will come online, or at least one, and I'll describe that mission, that will hopefully help bring this up just a tad bit. The comment I really wanted to make, though, is the NEOWISE camera, which is an infrared telescope. Now that's going to play a big role in one of the next missions that I'll talk about later on in the talk. But okay, so what is planetary defense? Well, it should be protecting the dinosaurs. Well, at least that's what the dinosaurs hoped back in time. But, actual asteroid impact didn't kill the dinosaurs, so we think it was originally thought that that's what it was. But it is now thought that the ejecta from the asteroid impact the asteroid hit, the ejecta flew up, did all its things, the global effects, and eventually, ultimately, wiping out our beloved reptilian friends. But the actual planetary defense is identifying it and mitigating potentially hazardous objects. So this could be comets, it could be, asteroids. I haven't really seen anything else besides those two certain objects that are flying around for planetary defense. But that's why we'll just focus on those two. But there, we need to also look into, okay, if we're identifying and mitigating potential hazard objects, what does that all mean? So identifying, initial acquisition, so our observations that we need to look at, and are there any kinds of algorithms or routines that we can do that'll help increase our chance of identification or discovery of an asteroid? Because right now we have this giant criteria of, we need to have so many observations of a target that create a tracklet, and then we need to have so many tracklets to create orbits, and so on and so forth. So we know that we're not just, seeing some type of radiation that's interstellar radiation that's hitting our detector, or if it's hot pixels or something strange like that. But now that's just the identification. We also go into mission design. So we're going to do, what kind of mission are we going to do to our target? Are we going to launch a rendezvous mission? Are we going to launch a flyby mission? Are we going to try to mitigate this target? Are we going to do ion beam deflection? Are we going to be doing a nuclear explosive device deflection or disruption potentially? Are we going to use a kinetic impactor? So like the DART mission. And it extends all the way to civil defense. So if a target isn't large enough, or if it's not going to be hitting in a highly populated area, or if it is, what do we look at for evacuation plans? So we look into those sorts of things, saying like, okay, if we have to evacuate Sao Paulo, what is it going to take? Like what are we going to need to do? How far do people have to get away? Like those sorts of things. And the list goes on. And the integration of a spacecraft components, and that's just a whole long list of things. So to help kind of focus at least the United States kind of idea of where we want to do, there's this plan that came out from the government, the US government, that's called the National Near-Earth Object Preparedness Strategy and Action Plan. That's a mouthful for me. I just call it the action plan. Usually folks ask what action plan, and I have to go in and say, oh, well, it's the Near-Earth Object Action Plan. But this goes through 5 main goals, so things we would like to achieve. So this goes right into the planetary defense. This is almost a better definition than what I tried to speak of on the previous slide. So, enhanced NEO detection. So again, that's different type of maybe ground-based observers. So do we need to have larger telescopes? Do we need to have another Arecibo that's out there? As in, do we need to, I won't say rebuild because I don't know if that's going to ever happen. But, maybe we need something that is more powerful than Goldstone. Goldstone has, it's part of the deep space network that we use for communication. And, it has radar capability. The problem is that it doesn't have the range like Arecibo have. So things have to be closer. Anyway, so that kind of goes into how do we enhance that NEO detection? Again, the tracking capabilities. And now characterization. So when we see something, now remember, the Arecibo observation of the Didymus system, you could barely see that secondary object. Well, barely is kind of a loaded word, but you could see that there are 2 objects. However, you're only seeing that particular geometry. So you can't get a full, I guess, glimpse at the full shape model of the primary. And I'll talk about that a little bit more. But now, so the NEO modeling, prediction, and information integration. So again, that could be the NEO deflection. Now, when you impact an asteroid, what kind of ejecta will we have? If we use a nuclear explosion device, how will that affect the target body? Will we have a lot of vaporization? Will it not do very much? Will we obliterate the target? Like, will it break up to a bunch of pieces? Or what happens if we use a gravity tractor? So having a spacecraft get really close and trying to pull it away using gravity. What's going to happen with these sorts of things? And that's goal 3. And then goal 4 and goal 5 are more of the, I would say, deep in the weeds kind of engineering sorts of things, because you're trying to include everyone for cooperation or inclusive efforts to how we can tackle these problems. And that's the same in the goal 5. So we are taking part in some international efforts now to see what happens when we acquire a target. What are the processes that we'll have to go through to try to confirm and those sorts of things. So there's so many moving parts. There's so many different engineers and scientists and politicians and lawyers that are all working together to try to tackle these goals or try to meet these goals. But that's not the only thing that we have with planetary defense. This past science decadal survey included planetary defense for the very first time. So that's very exciting for us planetary defenders, because usually planetary defense wasn't really something that people thought was real. You know, it's an insurance type problem. You know, when is an asteroid that's going to actually hit us? When is it going to be our problem? It's going to be in the future. Yeah. So they're kind of buying this is insurance. So it kind of boils down some of that. There were suggestions from the decadal survey to kind of look at rapid reconnaissance missions and look at more, looking at actual demo missions to help understand and test our capabilities, see kind of like, where are we at? How good is our insurance? You know? So it's kind of like you want to get a new roof for your house because yours is leaking, and you're like, okay, what kind of different roofs do I want? Well, I could use this one made of grass because that's a capability, but is there something else that we may have that might be better or be better in the future that we could be working towards? So just really excited about that. Anyway, so good news there. And there's other things in the political environment in the United States right now that would suggest that there are individuals at NASA and the higher tiers that are also excited about planetary defense. So hopefully we'll get some more things on that side. So okay, so kind of these concepts here. You got this nice, beautiful little GIF on the right here. This is showing some nuclear deflection scenarios, or at least a simulation that was done by folks at the Lawrence Livermore National Laboratory. So that's just one kind of mission that we might have as a nuclear explosive device mission. But there are other ones, like I mentioned before. We have rendezvous, and we have flybys. Those are the general kind of two types of missions that you can have, because with a rendezvous, you can have it be purely observing, like an OSIRIS-REx, if we ignore the whole touch and go. Same thing with Rosetta and the Hayabusa missions. Or we can look at more of a flyby. So we could look at DART. I would consider that a flyby, even though it impacted because you were coming in at hypervelocity speeds. But we can look at Lyzhoft, which was an observer that was an ESA-RAN spacecraft that flew by and observed the impact of DART. So we have all these different kinds of mission concepts. Now, this doesn't even get into the complexities of multi-spacecraft missions or anything like that. This is just single types of missions that can be done, a rendezvous or a mitigation mission. And the mitigation can have disruption or deflection. So yeah, it doesn't seem complex when you put it here, but when you start getting into the very fine details of how you need to integrate things, spacecraft component-wise, that can get a little tricky. So planetary defense missions, I already mentioned DART, and with the Lyzhoft, that was the very first planetary defense mission. We've had plenty, maybe not plenty, but we have had other missions that were looking at a scientific return, not a planetary defense engineering type return, as we'll say. So, for example, Deep Impact, with the impact of Comet Tempel 1. Now, it came in around 10 kilometers a second or so and had 3 correction maneuvers before impact, and I also had an observer to watch that. But that wasn't for planetary defense. That was intercepting a big comet. We wanted, DART is something that we used for testing our capabilities. So now we have OSIRIS-APEX, which is actually OSIRIS-REx, but an extended mission where OSIRIS-REx is actually going to be going to Apophis, which is an asteroid that's going to have a flyby with Earth on, well, Maybe I'll have to wait and we can discuss that a little bit more, but I'll kind of spill the beans here. It's Friday the 13th in April of 2029. So found that pretty funny, that anybody who's superstitious, there's your Friday the 13th. And then we have some future missions out there. Now, this is not all inclusive, of course, but we have Hera with a G, we have Satis, which ESA as well. And then we have, we'll call it the NEO Surveyor, which is actually the Near Earth Object Surveyor, which is a telescope. And remember how I asked you to remember NEOWISE? Well, this NEO Surveyor is kind of a successor to the NEOWISE spacecraft. So also maybe we'll have a rapid reconnaissance mission. So on the right here in these plots, these are just the different spacecraft mock-ups of the DART spacecraft as well as OSIRIS-REx. So the DART spacecraft, actually we could probably go on there, had I would say a pretty big camera. It's called Draco, had a rather large aperture at about 21 centimeters, and that was used for initial acquisition as well as the terminal guidance. So we were able to first detect the DART, well, not DART, the Didymus system about 60 days before, using about 243 stacked images with a 90-second exposure for this Draco camera. So that kind of gave us an initial kind of, hey, this is where our target is, to start doing our tracking and use that within our guidance filters. So I'll show that here later on, but we were able to hit this, our secondary object. I will say I did feel like it's kind of cheating because we kind of knew where our target was pretty well, but we were still trying to impact the secondary body, which was orbiting around the primary. So that kind of, it limited the uncertainty per se of our actual target, but we did have a higher order, I guess a higher frequency state change since we're in this orbit. Regardless, we were able to hit the secondary and change the orbit by 32 minutes. So we actually slowed it down by 32 minutes. So we can kind of we can kind of see here, the very far left image is of Lyzhoft Cube. I'm actually observing the impact of the DART spacecraft. And the two on the right are two different kinds of observations with time lapse of the impact, and the one on the far right is the actual tail from Dimorphos, so the secondary, and kind of seeing how that tail is streaming out. So the ejecta tail is what we'll call it. So DART has been, I would say DART is a very successful mission. We've gotten a lot of good science out of this particular scenario. But one thing I do want to comment on is, I know this is going to be my third time now saying, but if you recall that Arecibo image, that radar shape model, seeing the kind of the top-down image. Well, initially we thought that the primary body was more oval or more spherical-like, but you can see here from that far left image, it was more like an M&M or a Skittle shape, or more so like a peanut butter M&M shape. There's actually a colleague at APL who, with his kids, kind of looked at which candy is the closest shape to the primary body of the Didymus system, and it was a peanut M&M. So there's some information if you'd like, a little fun. I don't think it'll ever come up on any trivia, but now you know. Every time you eat peanut butter M&Ms, you're eating the primary body in the Didymus system. Okay, what about Osiris? I guess OSIRIS-REx, but now OSIRIS-APEX. Well, I mentioned that will be how there's the close approach of Apophis. Well, unfortunately, OSIRIS-APEX wasn't able to find a trajectory. Now this comes into the whole trajectory design kind of stuff that would be able to get us to Apophis before the Earth close approach, so we could observe any kind of movement on the surface. So we do get there after, and we'll do a whole proximity operations campaign. But yeah, that's going to be exciting. Not as exciting as I'd like it to be, to do a before Earth encounter and after Earth encounter comparison. But at least we'll still have a good, we'll have some good observations. We still might be able to see if there's any surface movement. But anyway, some of the GIFs that we see on the screen here, the bottom left collection, so the 3 there, are showing the touchdown and sample collection at Bennu. So this is where we came down, tagged, and then had our we just had our reverse thrust and push us out. Now on the far right, you can see that, well, that doesn't look good. It looks like there's particles coming out of the canister, and there was. So when we got those images down, we decided to go into emergency stow and stow our sample however it was. Initially what was going to happen was that the spacecraft was going to keep its arm out, and it was going to do a I guess a rotation maneuver to calculate what we'd have for the moment of inertia, to estimate what we'd have for the mass of the sample, because we have everything else calculated and calibrated, so we'd know what kind of momentum change that we'd have, or a moment of inertia change that we'd have. So yeah, that's kind of jumping around for OSIRIS Apex. There's just a lot of stuff going on there, and I'll kind of come back to the Bennu asteroid with some of our shape modeling efforts that we're looking at. So now I mentioned the Near-Earth Object Surveyor. This is going to be a telescope, an infrared telescope. We have found from NEOEYES, which was it was a infrared telescope that was repurposed for discovering asteroids, which was kind of fun. We found from them that the infrared is really good at detecting these sorts of objects. They're cold, so their peak emission is in the actual infrared band. So I didn't put any of those pictures up there, but are around 8 to 12 microns for a wavelength is what we really look at for general asteroid targets. Now, if you have a really high reflective body, then the visual band will still suffice. But generally, objects are pretty far away, and sending out light to 2 to 5 AUs and having that reflect back to Earth a few AUs, we have 1/r⁴ decrease for our actual received light, whereas with infrared we'll just have 1/r². So just a kind of a different signal profile. So let's get into the actual research at Goddard. We did a lot of that stuff at Goddard. Those are just the missions that have already been done and starting to come up. But we get into trajectory design and just general dynamics. So the general dynamics kind of the right, this is the first rendition of the Didymus system we're using an actual cluster to compute these dynamics, because it's a full 2-body problem. So it calculates the gravitational pull and torques on both bodies using polyhedron models in this case. But I prefer to use these collection of tetrahedrons, these triangular face shape models. And as you can see, this is more of a spherical object. This primary body, this is the Didymus system now. If you recall from those intercept images, it was more squished. And so, let's see if I can play that again. No, I can't. Great. And so that was just kind of indicating how we didn't have the particular observability that we needed to have to get the full shape model. So now we also are doing work with national laboratories. So that's looking at the different deflection types. So seeing what kind of velocity change we can get if we have a gravity tractor, if we have a kinetic impactor, if we have some kind of NED, those sorts of things. But we also are looking into the national laboratories and how we'd have for component integration. So if we're going to be using an NED, what are we going to need to have? What kind of things that we need to set up for integrating the device onto the spacecraft. We need to do all the vibration analysis and those sorts of things. So again, the deflection options. We need to look into what deflection option or which deflection options work for which regime. So by regime, I mean a time regime. So if we only have 2 years before an asteroid's going to impact us, I don't think a gravity tractor might work, because that might take decades to actually divert the asteroid's trajectory far enough away from Earth. Another thing we're looking into is understanding the return from a mission. So that is scientific, engineering, or what have you. Generally, when we do missions, we want a scientific return. So we go to an asteroid or a comet, we want to know the composition. We want to know origins of our solar system. We want to know, what I already said composition, but we want to know those sorts of things. But in a planetary defense mission, we generally want to say, okay, what is the state of our target and how big do we think it is? Because when we have those two, when we do a state uncertainty reduction, when we do a particular, if it's a rendezvous mission or a reconnaissance mission, we'll say, that'll help reduce our uncertainty of where a target would hit Earth substantially. And so I would say that's an engineering return. And if we are in a rendezvous mode, meaning we're loitering around our target, we can get a mass estimate. And so that really helps us say, okay, where is it going to be and how massive is it? Now you might say, okay, well, does that really matter all that much? Because what if we had a supermassive object, but it's made up of a bunch of cotton balls and would break up in the or burn up in the atmosphere? Well, that's a valid question. So that's when we get into shape models and composition and those sorts of things. And all of that does come down to system dynamics as well. So it's a very coupled problem. And generally, we've never done a pure engineering return, I would say, for a planetary defense mission, besides DART. We haven't, we've always wanted to return some scientific, something scientific, I categorize it as. So now, I kind of mentioned before about the spacecraft components. Well, that completely encompasses spacecraft environments. So why does that matter? Well, we got to worry about radiation. Where are we going? Are we going to be going, a half of AU to the sun? And if so, we're going to have particular shielding. What about when we are flying out in, 4 or 5 AU, what are we going to have for interstellar radiation? We need to have radiation shielding. So the more shielding we have, or the more security we want to have from that imparted radiation, thicker shielding that we need to have, which is more massive, meaning that we have to be able to have a higher launch capability, per se. So we also have thermal, which is part of operating your spacecraft. If your spacecraft gets too warm, you might have degraded sensor performance, meaning you might not be able to get as high resolution of imaging, or you won't be able to detect your asteroid or comet further enough out. You actually start having degraded signal to noise ratio, those sorts of things. Also look at micrometeorite. Well, why would you think of that? Well, if we get hit by a micrometeorite, that could be mission over. We might lose our entire system. So we do have a depiction of a Whipple shield and how that works. It's a few layers of a material that when another object hits it breaks up and reduces that imparted energy throughout. Obviously, if you have a big enough object, Whipple shield won't work as much, but it still reduces the amount that would be hitting your target. Now, vibrations. This gets into our launch vehicle vibrations as well as spacecraft vibrations. So when we do a maneuver, if we have flexible solar panels, there might be a flex mode that we didn't, or an oscillation mode or a frequency that we didn't account for, meaning that we may have pointing instability now, and we have to try to, how do we reduce that? Can we fire, or can we spin up some reaction wheels to try to reduce some of that. Is there dampeners that we need to put in our system that's going to be reducing the, increasing the mass that we need to have for our solar arrays? Now with launch, we need to say, well, are these things vibrating too much? Are we going to break something up on our spacecraft? So we need to worry about all of that. And so at Goddard, we are trying to look at the radiation, thermal, and micrometeorite environments. Since the spacecraft operation and vibration modes there are more of a, once you have a spacecraft design, you go further. But we don't have that point design now because we aren't designing to a particular target. And launch, we do have some vibration analysis done for our launch vehicles. So those are kind of not really full research areas, but environments that we do need to know. So trajectory design, I've mentioned that, we need to be able to get to our target, right? And the particular element that I'm more familiar with is the terminal guidance portion of it. So this is, when do we actually acquire our target? Do we need to do correction maneuvers? What is our state uncertainty? Do we do any kind of autonomy? These sorts of things. So if we are going to an unknown target or something that maybe has a pretty high or a low impact probability, meaning we have a, or at least something with a high uncertainty, we need to worry about when we acquire the target, how can we actually navigate to a location that would give us preferred observation geometry for a flyby or for a rendezvous. So that kind of gives an idea here on the right. These plots are, when we're running an extended Kalman filter along with a smoother to try to, predict where something's going to be, or the quality where something's going to be in the future, given its uncertainties, as well as how well can we reconstruct that particular mission here for a flyby. So how well can we reconstruct how far away we were from our target? And if we can reconstruct that relative dynamics quite well, we can get some geometry of our target pretty well known. So here I have target scale factor. So this is pretty much saying, if we are flying by this target, we should be able to nail down our target size pretty darn well. Now, there are instances where we won't be able to observe the entire object because during a fast flyby, we don't see the entirety of the object, at least in the visual regime. So we may need to incorporate infrared so we can start to kind of see that unilluminated side of things. The resolution might be lower, but at least still gives us some information of what that shape might be to help constrain volumes and start give us a reduction in our uncertainty of our mass. Because for a flyby, we haven't found thus far something that is reliable to estimate a target's mass when the target is small and when you're moving really fast. So this is a whole big problem that we're getting into, and we haven't really thought about this in this way. Usually it was trajectory design. Can we get there? What are the mass loads? But now we're getting into acquisition timing and what kind of instruments you need for that. So also in sensor simulation. So these are two different objects that I have simulated up. One of them is a kind of a silly, just a silly simulation of a visual regime. It's of a pretty low quality visible target. And on the left, this is an infrared representation. So it doesn't have the full heat transfer equations and things like that to help with any thermal inertia and things like that. This is more so just having an ambient type condition. So it's just supposed to be a representation and kind of seeing what kind of voltage change on a detector we might have for a given, here it's a microbolometer, but we also might have a MERCAD detector, which is a mercury cadmium telluride detector, which is more like a CCD or a CMOS detector. It's a light bucket, not a thermal change sort of thing. So, okay, this also gets into sensor fusion. So can we combine both of those and use that to help us inform kind of where we're going? So this is just kind of a little simulation of how we can start on the top one. This is a smaller object. We can start to see that a little bit, I guess, sooner than we can of the visual object on the left. So it's also incorporating some of the terminal guidance. So when we can see that, it's starting to use those measurements to update the Kalman filter about where something's going to be and where we're at to help inform where we need to be guided. So inform our control system to say, hey, we need to do a pulse or a maneuver that goes, this far, or maybe we need to slow down slightly. And so that's another area of research we're looking at, is kind of what we need to have for that. DART kind of have shown that the autonomy and this sort of thing is kind of on its way to, not going to say finalized, but there's been some really good research there to show, hey, look, we can autonomously guide ourselves to intercepting these objects. Now, that's about 150 meter object, the Dimorphos, and we kind of knew where it was, and we had favorable lighting conditions, but that didn't go into what happens when we have a smaller target and we have a shorter time to acquire our target, maybe only 3 days before, or maybe only 5 hours, and that. So that's another thing we're researching, is with that, how do we actually account for this timing? So another area of research is shape modeling. So shape modeling, like I was trying to allude to before, is very important for mass estimation, and which we should know the mass if we're going to have something's coming to hit us. So let's flip back real quick. Maybe it won't let me. Okay, I'll play them. But anyway, we started looking at techniques where we can use a onboard processor to create shape models. And so this is kind of our first attempt to be able to do that. Now, this was taken from the Benru approach phase images, so actual mission images, and used to create a shape model. Here's go to the next slide. You can kind of see here, this is how it works. It takes a sphere and uses images to get limb points to trim out or kind of create a shape. And that's really, really important, especially for initial proximity operations around your target. Because once you start to get a general shape of what you're doing, you can do different kind of navigation techniques, which increases the precision of where you are around a target, which, is very big in the planetary defense, especially if you want to map out how large something is or where you're looking. So from that, this kind of just gives the result that how this onboard processing works. We're able to ingest images, update our shape model as we got more images, and actually had a really good shape model compared to the 75 centimeter shape model that was obtained in OSIRIS-REx preliminary survey. And we do have some areas that were not observable. So you can see this kind of little boulder down here, and that was Ben. And so we didn't have the viewing geometry that allowed us to reduce the uncertainty around that actual boulder. Hence, we have these large tails that that were out on the end for the model difference. So so we're making progress there as well. That we start to do more things on board, and autonomy is starting to be a really big thing. So that's going to end what I have. Yeah, so thank you for letting me present. That's kind of some of the research that we've been doing. There wasn't much math in there. I tried keeping things more pretty picture-like, so we could have a further discussion now and those sorts of things. So if there's any questions, please let me know.
Thank you so much, Josh, for this outstanding presentation. It's a very nice talk. Thank you so much. So now let's open for questions and comments. So someone would like to use any question to Josh, please?
And it's any question. If you have any operations questions or things like that, I can try to answer those.
Okay, Jonathan? Well,
yes, I actually have some. Regarding the DART mission, how far are the findings related to what we're expecting, like what you were studying, what you calculated, and when you actually got the results and numbers? How far were you from the difference effect and
So
approach of the research?
that's a very good question. I actually had a colleague, my office mate, ask me, and we were hoping to get. I can't remember if it was. We were trying to get at least. I think it was. Oh, I can't quote the number right now. I don't know if it was at least. Was it 90 seconds or something like that for a change? That's what our mission requirement was for the orbit change. But with our calculations, I think we were getting up somewhere around 11 minutes that we were thinking was going to happen. So we were, from I guess our simulation thing, we were meeting our requirement, but I said 11 minutes. And if you remember what I said before, we got 32 minutes. Well, we also didn't have an understanding of what the momentum enhancement factor was. So momentum enhancement factor is when you impact an object, or at least an asteroid here, you're going to have some kind of ejecta that shoots out in the direction of where your spacecraft came from. And so we don't have a good understanding of planetary defense of what that number is for a target, because we don't know composition. We don't know how we're going to have particular interaction. And that's what the national laboratories are also looking at, is what kind of compositions will result in what kind of ejecta, which gives an estimate of this momentum enhancement factor. So we were estimating a momentum enhancement factor anywhere from, I think it was 2.5 to 3.5, which directly corresponds to that 3x or 3 times difference in our period change that we actually measured, the minus 32 minutes compared to the minus 11 minutes that we were thinking we were going to get. So yeah, that was definitely an exciting result and helped us really get a deeper understanding of what we don't know for this momentum enhancement factor.
Yes, thank you.
Mm-hmm.
Thank you, Jonathan. Someone else? Okay, I have a question, Josh.
Okay, be easy on me, Willard, please.
What is the current technological challenges in planetary defense mission, especially reference to the guidance, navigation, and control system?
So I would say one of the gaps that we have is initial acquisition of our target. So, and that's from actual hardware sense of things. So what kind of telescope are we going to need to acquire a target at a specific distance? And so that's, starting to push the sensor design. So what are we going to need to have to reduce our noise of our images as much as we can? To what kind of aperture size are we going to need, and what wavelength is the best? So that is, I would say, from at least a measurement perspective. Now, on the actual control and guidance side of things, well, guidance has been that mathematics, the mathematics there is pretty sound when you're using an EKF or some kind of a filter like that. Generally, that's pretty good, but maybe there needs to be more robustness to certain things. Generally, when we do a fast intercept mission, we're coming in really fast, and we're very close to linear regime of things, so we don't have to worry about the EKF starting to diverge due to the nonlinear elements. And so the other thing is actual spacecraft control capability. So if we get this kind of measure and we get an estimate where something's going to be, how precise can we get that maneuver to retarget that location or to change our trajectory to impact where we need? So that's another sort of thing there. And that's why we kind of, we do look at, Monte Carlo analysis for those sorts of things. Another element is data rate. So if we're going to be intercepting these things, there's no way we can downlink all of these images and do all of our trajectory maneuvers at the end. That's why Dart works so well with the autonomous system. So in the GNC type of deal, those are kind of our needs of research is, instrument, spacecraft control capability, and data transmission. The DSN works great, but it's a bottleneck because of it's being congested. So. And there were some questions in the chat as well, I think. If I answered your question, Willer, in a good enough way.
Josué?
Yes, there's a question by, thanks Josh for your presentation, very nice talk. And I'm starting a research group on asteroid dynamics here.
Okay.
Probably worked with Dan Shears, he was my supervisor in Boulder, TU Boulder. So now I'm a professor in the campus of University of Colorado System, the campus in Colorado Springs. So I would like to discuss a few different things with you regarding even potential collaboration.
Okay.
But I have two questions. One is more generic. I think the public would be interested to ask you this.
Okay.
That if there's any interest of the current missions that are, you've mentioned Hayabusa 2, Osiris Apex now, regarding the 2024 YR4 asteroid that is being the news.
I can't speak much on that, except for what's currently public, but that actually has been a hot topic that we're looking at during the first initial measurements, and we're having a relatively higher than desired impact probability. So we were looking at different kinds of trajectories that could work for one, a dedicated mission, so a launch from Earth, or two, repurpose missions. So if we had to repurpose Apex or Lucy or any other space mission or spacecraft that we have in space. So that's kind of what we were looking at in that sense of
possibilities.
Could we get there?
Okay.
And if so, can we get there before 2032?
Okay.
So now we're looking more, now the impact uncertainty ellipse is off of the Earth. So we're at a very low impact probability now. And now we're actually looking more at a lunar impact. So that probability has increased to around 2%.
Okay. So yeah, because I'm interested in doing some research regarding that asteroid as well. So because my two students now, they're currently focused on in Apophis. So, but I could redirect the interest or split the interest for this asteroid. So this is something that eventually, if I can get in touch, I'd like to discuss with you. Yeah. And the other question is related to Apophis, by the way, because as being part of Apex and maybe you're collaborating with Hayabusa 2, I assume. I was in JAXA, so I know Tsuda Sensei is the PI.
Okay.
Hayabusa 2. So, and I was trying to follow what they're doing. It was interesting because I have several colleagues working on the dynamics of Apophis for these missions, and one of the things that they always bring to me is the instability of the rotational axis of Apophis and how you're handling those difficulties. I think it's part of the question of Wheeler regarding the technological challenge and even the modeling and dealing with the dynamics.
So that is something that's very interesting. I think the fast period of Apophis is around 32 hours. I'd have to go back and look, so don't quote me on that. And a long period, I think, is in the hundreds of hours. So, yeah, the non-principal axis rotation does play a challenge, but we've seen that before. So the Rosetta mission at Comet 67 PCG, actually, Comet 67 PCG was a non-principal axis rotator. Very close to principal axis, but every few months they did update their C kernels or their attitude kernels of their target to kind of readjust to that new I guess, orientation axis per se. So a rotation type axes, or to help, this kind of help where you're looking, or where the orientation of the object. So I haven't spoken with the folks at Kinetics about how they're planning on doing that for their op-nav. But that is something that I could probably ask and see what they're planning on doing. If they're just planning on taking a bunch of images, turning it into this shape model generator to say, okay, this is where we're looking, and then taking subsequent images thereafter after we have a shape model saying, oh, this is where we're looking. 1 hour later, here's where we're looking, and kind of building up that model as they go and seeing if they can do some good prediction models, at least in the shorter term.
Yeah, because I've been discussing these details because I'm doing this approach of modeling the dynamics with Apophis, and especially when you have the close approach to 2029, it's going to be so challenging to model all that. So on that, specifically in the close approach.
Yeah, so one thing you can look into is a program called GUBAS, so GUBAS. That was written by Alex Mayer, I think, also at Boulder. I might have been actually underneath Dan Shears, but anyway, that was what was used for the binary asteroid dynamics of the Didymus system, and it's a full two-body problem. So you might be able to look into that. Now,
could you spell again, please, the name?
GUBAS, so GUBAS. I guess I could probably write that in the chat too.
Yeah.
Let me get over to the chat, because I think there's also some questions.
We can check with Dan as well. So, but thanks for the indication, the recommendation. I didn't know about that.
Yeah. I definitely look into GUBAS. It's because that's a full two-body problem. Right now, it doesn't do principal axis rotation, so you'd have to add that capability. Okay.
Okay, great.
Yeah.
I know he had some PhD students that have been working on this, and also his the other colleague, Jay McMahon. So I know they have people working on that.
Yeah, Jay. Yeah, that's good. Yeah, no problem.
Thanks.
All right, so in the chat we do, is there any NED mission planned? No. And the reason for that is we have a kind of a treaty in place that we can't weaponize space. And so a lot of colleagues, we're just going to say, not even international, we have people in the States as well that are saying, well, can we actually do that? Should we do that? Are we breaking treaties? Are we breaking laws? So at the moment, it's not planned. But we are still researching what may need to be done during one of those missions, if we need it. Because if we have an asteroid coming in that the only way we can deflect it is by a nuclear device, and we're going to have millions or billions lives lost, I can assure you that we're not going to hesitate to use, well, there'll be some hesitation, but we'll greatly consider any option that will reduce the casualties. Okay, so another thing here from Johan, I guess, Jonathan, or Jonathas. I'm so bad with names. I guess Jonathas. Better? I don't know. Anyway, that's about.
Don't worry about it.
I'm so bad. How can you please pronounce it for me? I'm really bad. Fine.
Just call John.
Right,
John, that's fine.
I appreciate you working with my innovators. All right, John. So, as you're saying that this is an onboard processing capability, yes, it very much is. We do have techniques that kind of work around that by reducing the actual data that's processed. So in the DART mission, we didn't take a full frame and process that. It actually was cropped down to, I think it was a 512 by 512 image, when the original was up into the 2000 pixel by 2000 pixels. So around the 4 megapixel size of things. OSIRIS-REx, when it was doing its tag, also had a reduced imaging plane, but was able to do particular hazard avoidance based off of some map overlaying and things like that. It was able to be ran in real time. So we do have limitations. Now, the stuff I mentioned before about image stacking to do initial detection, we've only ever done that on the ground. So that's another area is how do we have the processing to align images, to stack them, and to do some of the image processing and those sorts of things. And that is a very, very that's a challenge.
Thank you.
Mm-hmm.
Oh, I'm back. My internet connection was lost here. Sorry for that.
Back, Willer.
Can I have just a minor clarification, Willer? Josh, just to be sure, I was checking here the GUBAS package that you mentioned. Is this related to modeling the full bar problem Earth's Apophis, right?
No, so this was used initially for the Didymus system. So
Didymus, okay.
Yeah, so you would have to add in some external forces such as atmospheric drag. Right now, there are some functionality for tidal forces and those sorts of things. There is no deformation capability, so you might have to add that in. So that's one way. The other option you can do is look at mascons and just see how a bunch of mascons deform when they go by.
This is what I'm doing with students. So multi-layer mascons models. So.
Yeah, that's another way you can look at it.
Okay, thank you very much.
Of course.
Josh, I have a question regarding a hot topic, that is the artificial intelligence. I know you said that you have a problem about the issue regarding the processing on board, but have you planned to use in the future AI somehow on board the satellite to process images, or I don't know?
So I like machine learning techniques. I think they're great, but they break down when you see something you didn't train it with. So for example, for image recognition. Well, first I'll step back. There is current research that is using machine learning for SLAM approaches. So, creating maps of your target as you go around. So it's creating features of your target, and when you can re-see these features, you start to be able to put together a shape model to help those sorts of things. But now, what happens? Oh, well, the example I was going to give with the image recognition, there's been instances out there where they trained a machine learning neural network to identify a tiger. Well, you can put glasses on that tiger, and the tiger won't be recognized anymore, and it'll be maybe thought to be a pineapple, those kinds of things. So if you ever get outside of your trained set of data, you could start to fall apart. Now, there is physics-informed neural networks. That's some research being done by folks here at the University of Maryland. So that helps use physics to constrain the problem to help increase the accuracy of extrapolation. So they're using it primarily for gravity modeling. So what we have for Earth, we have giant spherical harmonic models, 100 by 100, 200 by 200, but that equally samples the entirety of Earth. Now, this physics-informed machine learning can say, hey, we don't really need to have large sampling around this very flat, evenly, mass-distributed area, because in this area, the density is the same, or at least the gravitational effect is the same. But now when we get into mountainous regions or regions that have valleys, that's when we need to sample that differently. So it kind of helps you understand where you need to sample something. So there are applications. Again, I'm just fearful when you use machine learning techniques for acquisition or target determination. That can be bad. Now, you might be able to use target or machine learning processes to help you filter your image, so reducing noise to help pull more out of it. Now, I could see that being used, but you still have the targeting algorithms and stuff like that that need to be ran on some measurements. So the way I think of neural networks and machine learning is that it's just a giant filter that have all these different things. That's kind of like how our brains work. We see a water bottle. We understand it's a water bottle. We're filtering out what that is. We're accessing our database in our brains to say this is a water bottle. Or someone else might see it and be like, it's not a water bottle. I don't know, it's a tree or something. But that I think it has application. I just think we have to be careful in blindly applying these techniques.
Right, it's very interesting. Thank you. Adriano, please make your question.
Are you reading me?
Adriano?
Hello?
Yes,
Yes.
I can hear you, Adriano.
Listening? All right. Congratulations to your presentation. And I have a question about the simulations in local. The instrumentation for this kind of mission, considering that we have a small amount of missions related to that kind of scenario mission. Would it be worth to simulate for this kind of mission by a kind of 6-axis gimbal or a couple of robotic arms to simulate the mission scenario, or fully simulated is worth?
So in these particular missions, for initial understanding, I don't think you have to go into full detail in these simulations. I think, at least for the imaging sorts of things, you could probably just have a strapped down imager, so you don't have to have any gimbaling on that. And it's just do initial acquisition understanding. I don't think you have to do 6 degrees of freedom understanding at the initial kind of feasibility study, because in these missions we're not needing to slew very fast. Because if we're trying to impact something, that's just going to be pretty much missile guidance. So that's pretty standard for those sorts of things. We just have to worry about, since we're coming in so fast, how precise do our maneuvers need to be? So how precise are our on-off for our thrusters? Now, when we're doing flyby missions, we'll have to have some gimbaling, and there we might be able to do a first look at just a general angular rate for flybys for an understanding for the dynamics. But when you do get down into full mission generation, you will simulate 6 degrees of freedom, all the torques, all these sorts of things, any articulating arms, any kind of gimbaled platform for your sensors and things. And mind you, that all adds complexity. And so in these kinds of missions, it's better to have reliability. So the less moving parts, the better. Now, developing that 6-DOF capability, I think, is a really good thing to have, just in case, when you do full-up missions. I know for one of the missions that I'm working on now, there's a full 6-DOF simulation that looks at torques and all those sorts of things. It needs to have that. Does that answer your question?
Yeah, in general, we can see that the initial data is crucial to the success of the mission. And simulation, when we try to simulate it in real time with mechanical components, would increase the complexity of the simulation. And that was my question. I think it's answered.
Yeah, okay, good.
Thank you.
Yes, thank you for the question.
Thank you, Adriano. So is there any other question, comment? So thank you again, Josh.
Of course.
It was a great pleasure an honor to have you here in our opening of our seminars this year, 2025. So thank you for your time, for this outstanding talk. And if you have some words to conclude here our seminar, please
Okay.
go on.
Yeah. So if anyone wants to get in contact with me, I think you have my my NASA email. If not, you have my personal email. So if anyone asks, you can feel free to distribute that, and we can further conversations.
Yeah. Okay. Well, thank you so much. Also, thank you everyone for having here today, and I wait you for the next seminars here at the E2MoC Research Group. So have a nice week and good afternoon, everyone. Bye bye. Thank you.
All right, see you, everyone. Thank you.
Bye.